Hello. Climate risk affects home insurance premiums because when a region becomes more prone to catastrophic weather events, insurance companies raise premiums there. And this negatively affects mortgage payments by borrowers, increasing their monthly payment burden, and that in turn affects the bank's liquidity. The bank is hit again by the devaluation of its assets since it owns the properties until they are paid off. The objective of my capstone project is to forecast the near-term effects of climate on insurance and home price index. So these can be factored into mortgage rates to mitigate the risk mentioned earlier. Today I show you how I use ARIMA and LSTM to predict home price index. ARIMA is a linear model that uses autocorrelation to predict future values from historic values. Long short-term memory, which is LSTM, is a deep learning recurrent neural network designed for modeling complex nonlinear and long-term dependencies. So the approach was to use LSTM from PyTorch as a primary multivariate model, while an ARIMA model from STAT model was used to forecast the predictors. I used clean climate data on flood, heat, drought, and fire from year 2000 to 2020, splitting it into 80% training, 10% validation, and 10% test data. And it was also very necessary to ensure the data was not randomly split, as that will remove temporal information from the model. So the conceptual architecture is like this. We have the historical exogenous variables. We use that to train a multivariate LSTM. Then we forecast the exogenous variables. So the data was up to 2020. We forecast the exogenous variables to 2025. Then we feed that into the trained LSTM model to predict the HPI. So I'll take you through the code now. So I'll go over the most important parts of the code. This shows the variables I used for the modeling, the climate variables. This is the ARIMA function. It forecasts one variable at a time. And then this uses the ARIMA function to forecast all the variables. This is the model itself from PyTorch. This is a training function, and I would like to highlight two main things here: the early stopping check and the saving of best checkpoint. So during training, what we are aiming at is to reduce the loss. So after every epoch, the loss is supposed to come down. You may have a trend where it comes down, then it starts to go up again. Then as it goes up, it could start going down. So there should be a point that you say you've gotten the best value and it's not getting better. You should also give it some time so that if it can start going down again, you don't prematurely stop it. So that's where we have the patience counter. This by default is 20. And what it's doing is that it's saying how many worst results are we ready to accommodate before we stop it. And this is to make room for a situation where it goes up and goes down again. But if it continues going up, then we stop it at 20. So it's counting 20 bad or worst results after the last best result. Anytime that the result we get is lower than what we have saved as the best, we save the new lower result as the new best result, and then we store the weight at that time. So that is saving the best checkpoint. And what that allows us to do is that, let's say it goes bad for the next 20 epochs after the best one was saved, we are going to stop. But when we stop, we want to come back to the result we had when we were at the best loss. That's why we save the checkpoint. These plots help us visualize what's going on during the training. This one plots the predictions, and then this one plots the losses, so that we're able to visualize that. And I'll show you that later. So this runs the pipeline. This is where we start running the pipeline. We import the file. This is where the training is done. And in this case, you see that I've asked you to do 4,000 epochs. And we can also see that the loss steadily goes down. At some point, it goes up and then goes down again. This is one case where it goes down all the way to 661 and jumps to 1008. But you can see that it goes down again to a value lower than what we had before the jump to 1008. So this is the validation prediction chart. The predicted values are in orange and the actual values are in blue. You can see that there's quite a very good overlap. That means that the predictions were really good. And this is the loss curves. It goes down, and you can see that by the time we reach 4,000, we are kind of plateauing. It's really gone down. These are the metrics we got. 0.9 for R squared is good, and the RMSE of 5.5 is also good. So I then try to forecast 4 years. Basically, the training was done with data up to 2020. So 4 years would be 2021 to 2024. And so this is the result. So you can see 2021 to 2024. This is for just the first 10 to see how it goes. And we have the predictions here. So this is an overview of the code and the steps I took to do the prediction. So to conclude, I'll say the main challenge with the prediction is that the patterns in the training data should be similar to the patterns in the predicted time period. If there are drastic changes, for instance, due to other economic factors, the predictions will be either overestimated or underestimated. The predictors can also compound errors. So this approach is not appropriate for very long-term predictions. Predictions up to 7 years are good, with diminishing accuracy as we approach 7. Generally, using these two models will produce good results if the patterns remain similar between the historical and then the predicted time period. Thank you very much.